Good afternoon to everyone. I welcome for my lecture today. Let me introduce myself first. Myself is Dr. P. Amaladass. I am working as a professor in the Department of Chemistry in Madanapalle Institute of Technology, deemed university. Today, I would like to talk about a topic on addition reactions. It is a general topic in organic chemistries. During this particular lectures, you will learn about the definition of the addition reaction, and then the types of addition reactions, and then examples of addition reactions, and the fourth one is this mechanism, and the last one is an applications. So I'll repeat again. During this particular lectures, you will learn about addition reactions. The content of this particular lecture is definitions and types of addition reactions and examples of addition reactions and mechanisms, and followed by the last one is an applications. So you will, by the end of the lecture, you will come to know this idea about this complete of addition reactions. So now, what is first the definition of this addition reactions? Addition reaction is a reactions in which a combination of the two reactants to form new product of a single product. So that is this addition reaction definitions. That means it occurs combination of two reactant to form single product is called addition reactions. Examples: A, reactant A and B, they react together and form the product C. If you mathematically express this particular reactions, you can say this 1 plus 3 equal to 4, a single product. So it is a combination of these two different reactants and form a single product, and that is called as an addition reactions. And further, the most significant point for this particular addition reaction is pi bond breaks here, whereas the sigma bond, the new sigma bond is formed in this particular reactions. So during the addition reactions, the pi bond breaks, and then the new bond which formed is this sigma bond, the new bond is formed here. So the addition reaction, the definition starts as a combination of the two reactants and form a single products. And significant point, the pi bond breaks, whereas the sigma bond, the new bond, sigma bond is formed in this particular reactions. It's about this definition of this addition reactions. And then in the next one, we will move to this, the types of addition reactions. Addition reactions are classified into mainly three different types. The first one is this electrophilic addition reactions, and second one is this nucleophilic addition reactions, and third one is this free radical addition reactions. I'll repeat again the types of reactions. Types of reactions under addition reaction. The first one is this electrophilic. So there are three different types. One is electrophilic, nucleophilic, and final one is free radicals. So how this named exactly? It's based on this attacking species. So attacking species, if the attacking species is electrophile, then it is called as an electrophilic addition reactions. Suppose if the attacking species is a nucleophile, then it is called as a nucleophilic addition reactions. And if the attacking species is a free radical, then it is called as a free radical addition reactions in these cases. Okay, so it's all mainly depends on this attacking species. For electrophilic, you can say this electrophile. And for nucleophilic addition reaction, it is based on this nucleophile. And third one is this free radical. Free radical. Okay. Before going detail into the each and every type of this addition reactions, first we should know the basic concept. Then only you come to know this. First, you should know what is an electrophile and what is a nucleophile and what is a free radical. If you understand this concept, then only if you go into the deeper, you can understand the different types of addition reactions. Otherwise, it is impossible to understand. So let us discuss one by one, and this what is electrophile and what is nucleophile and what is free radical. Then I will go into this detailed discussion of each and every types of addition reactions. So electrophile first. So electrophile, the word which is derived from the Greek word. Okay, so that it can split into two. So it's electro means is an electron, and phile means loving. So electron loving species is called as an electrophile. I repeat again, the electrophile, the word which originates from the Greek word, you can split into the two. Electro is one part and phile is in another part. And electro is called as an electron and phile meaning is loving. So electron loving species. Electrophile. Or otherwise electron deficient species. Examples, it can be further classified is as positively charged electrophile. Examples is you can say this carbocations and then NO2 plus. So this is our positively charged electrophile examples. One is you can say the carbocations, the carbon having a positive charge, or otherwise NO2 plus. These are all. And then the second type of this neutral charged species, neutral charged electrophiles. So it can called as BF3 and aluminum chlorides and FeCl3. So these are all is Lewis acids, and these are all considered as neutral charged electrophiles. So electrophile, basically, it is an electron deficient species, or otherwise it is called as an electron loving species. The examples I've written, the carbocation, NO2 plus, or neutral species is like a BF3 and aluminum chloride and then ferric chloride. These are all comes under this example of this electrophile is this. The next one is I'd like to move to this nucleophile. The next one is called this nucleophile. This is otherwise is called as an electron rich species. Electron rich species is called as an nucleophile. That is this definitions. Here also you can classify it into the different categories. Negatively charged nucleophiles. Another one is this neutral nucleophiles. Okay, so the first one is you can say this negatively charged nucleophiles. There's, for example, OH minus and Cl minus and bromine minus, etc. And this neutral charged species nucleophile, okay, for example, water in ammonia and H2S. These are all considered as examples of this neutral charged nucleophiles. So the nucleophile in simple electron-rich species, and this may examples are here OH minus and Cl minus and Br minus, and also neutral charged nucleophiles. It is water molecule, ammonia, and H2S. So this is talks about this nucleophile actually. The next one is a free radical. So here any atom have a single electrons. It's usually the free radicals will be obtained by this homolytic cleavage. For example, you have this the bromine, it will be undergo this homolytic cleavage, you will be getting a Br dot. So this is usually called as a free radicals. That's an atom having only one electrons, and this usually obtained by this homolytic cleavage of these bonds, and thereby you will be able to get this radical species. You can examine Br dot and then Cl dot and then hydrogen dot is whatever it cases. So it's all called as a free radical. So we should know the basic concepts before going into the detail about these types of addition reactions. First, we know electrophile, an electron deficient species, whereas next is a nucleophile, an electron rich species, and free radical, it will obtained by this homolytic cleavage and this atom having a single electrons. So these are some of the basic concept before going very detailed into this, especially this addition reactions. Now I would like to move to this, the types of addition reactions in a very detailed manner. Since we know now the basic concept of this electrophile, nucleophile, and free radical, we would like to move to this addition reactions in a detailed manner types. So the first one, we will see this electrophilic addition reactions. The first type is electrophilic. So the definition for this particular electrophilic addition reaction is, it is a reaction in which the electrophile attacks the unsaturated carbon and pi bonds breaks and sigma bond is formed here. I'll repeat again. The electrophilic addition reaction, it is a reaction in which electrophile attacks the unsaturated carbon and add across the pi bond, and pi bond breaks, and thereby the new sigma bond is formed. That is called as an electrophilic addition reaction. So the attacking species is an electrophile attacks unsaturated carbon. Thereby, you'll be able to obtain pi bond breaks here. And sigma bond formed. This particular reaction mainly occurs in alkene and alkyne. This particular reactions mainly occurs alkene or otherwise alkyne. So alkene is a functional group double bond and alkyne is the triple bond. So here mostly the electrophilic addition reaction is occurring. So here when you go to the examples, again I further classify into two different types. One is symmetrical case, another one is an unsymmetrical case. So the first one is, I can write it as symmetrical, and then other one is this called as an unsymmetrical case. So first I would like to give the example for the symmetrical case. In the case of electrophilic addition reactions, you have to take this molecule of this ethylene and add HBr and you'll be able to obtain the product of ethyl bromide. This is for the symmetrical cases. Whereas when you talk about this unsymmetrical cases, the second one you talk about unsymmetrical. In this case, you take this propene and add HBr, and you will be able to obtain isopropyl bromide. So there are two cases, one is symmetrical, another one is in unsymmetrical cases. In the symmetrical cases, I took an example of this ethylene, and then it will be added to this HBr, and you'll be able to obtain the product of ethyl bromide. In this unsymmetrical case, you take the propene, it adds to this HBr, and thereby you'll be able to obtain the product of isopropyl bromide. Okay, so here an important point you have to notice. So when you add this HBr to symmetrical cases, you will have a chance to get only one product. You have a chance to get only one product, that is ethyl bromide. Whereas when you go for an unsymmetrical cases, you will have a chance of getting theoretically two products are possible. But which product is practically is obtained, that we have to see now. That's why unsymmetrical case is very important, especially when you compare this compared to the symmetrical case, the case of electrophilic addition reactions. So I'll explain the unsymmetrical case very detailedly, and then also we can see the complete mechanism of this electrophilic addition reactions on this particular case. So let's see the unsymmetrical cases now. So then we will be able to explain here. Okay. Here, only one product I wrote, but theoretically, there are two products is possible here. One is propyl bromide, another one is this isopropyl bromide. So, there are two possibilities when you add the HBr into this propene. One possible product is isopropyl bromide, then another possible product is this propyl bromide. Theoretically, I'm talking, but practically, you usually get an isopropyl bromide. Then now we can see in what concept this addition was undergoing, so that we'll be able to obtain only the isopropyl bromide and not this propyl bromide. Okay, this addition is happening, that means HBr adds to this that propene based on the rule called Markovnikov rule. That is very important. So it is called as this Markovnikov rule. Based on this particular rule, the HBr adds to this propene system. Okay. So what the rules talks about? The rule talks about this. The negative part of addendum adds to the carbon which containing less number of hydrogen atoms. That is the main things. So Markovnikov rule, I repeat again. The negative part of addendum adds to the carbon which containing less number of hydrogen atoms. For example, you take this H plus, that is Br is minus, say delta plus and delta minus. So that delta minus is add to this propene. Adds to this propene system. Okay, so which carbon this delta minus will be attacked, whether this carbon or this carbon. Okay, so when it will be added across the double bond, there's no doubt, but which carbon this delta minus, the negative part, will be added. So according to the Markovnikov rule, the bromine minus, that means the negative part adds to the carbon which contain less number of hydrogen atoms. So you can see this, the CH, this particular carbon where I'm just showing that carbon having a less number of hydrogen atom here. So bromine will be added to the CH, not to the CH. So that the product will be CH and CHBr and then CH3. That is why we are able to get this particular product. Suppose if it doesn't follow that particular rule, then the opposite way of forming is CH3, CH2 and CH2Br. But the system is following here Markovnikov rule. So obviously the product isopropyl bromide is the only product is obtained for this particular reactions and not this propyl bromide. I hope you understand. So the addition of this HBr to this propene based on completely Markovnikov rule additions. That means the negative part of addendum adds to the carbon which containing less number of hydrogen atoms. That's the rule it follows, so that we got an isopropyl bromide. So now we can see about this mechanism of this particular electrophilic addition reactions. Mechanism of this particular reactions. Here the mechanism, it follows the two steps, step 1 and step 2. Step 1 is the formation of the carbocation, and then step 2 is the attacking of this nucleophile with this particular carbocation. Okay, so there are two steps here. Step 1, formation of carbocation. Formation of carbocation. So the step 2, attacking of nucleophile on carbocation. Okay, so step 1 it is there. So formation of carbocation. We'll take the examples. Propene itself, add H plus, and you'll be getting this. So when H plus is added, the first step to the propene, and you'll be getting isopropyl carbocation. Okay, but here when you note this point, one more carbocation possibility is there. For examples, when the H plus, instead of adding here, suppose if the H plus is added on CH carbon, then if you added CH carbon, your product will be CH3, CH2 and CH2 plus. So this is called as, this is isopropyl cation and this is propyl cation. So one is an isopropyl cation, another one is the propyl cation. So among these two, which one is possible to form? Obviously, the isopropyl cation. The reason behind this one is this isopropyl cation is secondary carbocation, whereas the propyl cation is a primary carbocation. So we all know that's the stability of the carbocations. When you look at this, tertiary is the most stable, then secondary, then the primary. So according to the stability of the carbocation, you can see the secondary and primary possibility is there, the formation. Obviously, the secondary carbocation is the most stable. That is why only the isopropyl cation is formed, not this propyl cation. I hope you understand. Okay, so why this tertiary is most stable? Because of its hyperconjugative resonance. Hyperconjugative resonance, otherwise called as a no bond formations. Okay, so you know this from the step 1, the formation of this isopropyl cation is formed. And moreover, the step one is the slow step, and that step is called as the rate determining step. It is a slow step, and this particular step is called as this rate determining step. So once this carbocation is formed, the next step is very fast. That's why the formation of a carbocation, only this whole particular mechanism, that rate is depends on the formation of the carbocation, nothing else. Okay, this is about the step one. And once this carbocation is formed, the step two is this. Obviously, the attack of this nucleophile, the Br minus on this particular carbocation, then we will be able to obtain the products. Okay. So the Br minus attacks to this isopropyl cation, and there will be we will be able to obtain this isopropyl bromide. So step two is the fastest step. The fastest step. I hope you understand. So the mechanism involves these two steps. The step one is the formation of this carbocation, and that step is the slow steps. And that particular step is a rate determining steps. Whereas the step two is an attacking of the nucleophile on the carbocation, and thereby we'll be able to obtain particular product. And this product, so step two is a faster step. It's not a rate determining step at all. Whereas the only step one is the rate determining steps. So in step one is there a possibility of this two different carbocations, and among the two carbocation, which one is the most stable carbocation that has a possible to form compared to this another carbocation. So in this example, what I have took this propene cases, an isopropyl cation is the most possible formation of the carbocation because of secondary, and that is the most stable compared with this the formation of the primary carbocation possibility. That will be completely neglected here because of primary, it's the least stable one. So I hope you understand the electrophilic addition reactions that involves the two steps. Okay, that I have shown now. One is a slow step, other one is the fast steps. I hope you understand. So like this, you can take the many other examples, and you can also work it for to understand the mechanism of this electrophilic addition reactions. Okay, fine. And the next one is this applications. So there are a lot of applications. One is the preparation of an alcohols. Preparation of an alcohols. And second one is the preparation of an alkyl halides. And then pharmaceutical, say for example, medical related derivatives. And for fourth one is an industrial process. Like that, you can tell the so many application of this addition reactions. So one is the industrial process. Many times people use it, this electrophilic addition reactions types for the industrials, and you can prepare many type of different alcohols, and also mainly the useful of the preparation of this alkyl halides. It's one of the major uses of this particular addition reaction, especially electrophilic addition reactions is major uses for this one. And then next you can say this medical related derivatives or pharmaceutical intermediates, etc. And then industrial process also. So this is what's about this electrophilic addition reaction is completely in this one. And then next I would like to talk about this nucleophilic addition reactions. So in the type of reaction, three types. One of the reactions I have explained now, one of the reactions. Next, I would like to move to this nucleophilic addition reactions. So nucleophilic addition reactions. So here the definition itself talks, we already seen. The attacking species here is a nucleophile. So the nucleophile attacks to the carbonyl, especially aldehydes or ketone, to form their corresponding product. That's mean pi bond here also breaks and the new sigma bond is formed. So the attacking species in the nucleophilic addition reaction is absolutely a nucleophile. So it mainly involves in aldehydes, or CHO, or the ketones. In this case, the nucleophilic addition reaction, it is formed here. So examples of this nucleophilic addition reaction is base catalyst of HCN to form cyanohydrin, example. For examples, you can see that or C or double bond O plus an HCN, the presence of a base, and you'll be able to obtain cyanohydrin product. So the example for this nucleophilic addition reaction is base catalyst of HCN to form a cyanohydrins. So for example, ketone, the functional group is RCR double bond O, and HCN in the presence of base, and the product will be the pi bond will be breaks here, and the new sigma bond is formed, the CCN bond will be formed here. And this is called as a cyanohydrin. Okay. We will see now the mechanism of this particular nucleophilic addition reactions. It also involves two steps. Okay, the step one, it's a step one is possible to form this. We can write it RCR double bond O. Before that, actually, in this case, is first the base has been formed. For example, the base will be reacted with an HCN and to form Cn minus and water. First, this is generation of the base. Nucleophile has to be generated here first. The base reacts with an HCN. It will be generate the nucleophile Cn minus and water. Then the step one, it talks about this ketone molecule react with a nucleophile. And the nucleophile attract to the carbon, since the carbon is electron deficient here, and thereby the product is Cn. And step two, it is simply RC or cyanide and O minus, that will be reacted with this H plus, and you'll be able to obtain Cn. So this is the mechanism of this particular reactions. And the first step is this once this nucleophile is generated with the help of the base for this particular reactions, then this base will be started to, nucleophile starts to react with an ketone. Here the C double bond, the ketone, the carbon is electron deficient here. Then this nucleophile attacks the carbon and you will be able to obtain this product. Then after that, then the reaction of this particular intermediate will be reacted with an H plus and form the corresponding cyanohydrin product. So this is the mechanism of this nucleophilic addition reaction. Mostly involves this aldehydes and ketones, and thereby the pi bonds breaks and the new sigma bond is formed in this particular case of the reactions is also. So here the application of this nucleophilic addition reactions, also the formation of this pharmaceutical intermediates, an application wise talks about The first one is this, industrial intermediate. Industrial intermediate. Or the second one is talks about this medicinal derivatives. And etc. There are other reactions will be there. So this is also have a lot of applications of this particular nucleophilic additional reactions. And the last one we will talks about this free radical addition reaction, the third ones. It talks about this. The last one is this free radical addition reactions. Free radical addition reactions. So here the definition starts about this reaction in which the attacking species is a free radical which attacks on this alkene or alkyne, and thereby pi bond breaks and form the new sigma bond product. So the attacking species here is a free radical in this cases. So free radical, we know that it's obtained by this homolytic cleavage usually. Okay, so the example for this free radical addition reaction is examples. I'll take again this propene system. For example, peroxides. Okay. So the example for this particular free radical reaction is, so take the example as a propene that will be added to the HBr in the presence of peroxides. Okay, so then the product will be propyl bromide. In this particular cases, the HBr adds to the propene is not Markovnikov rule, it follows an anti-Markovnikov rule. So that is very important. So in the case of electrophilic, it is forming an Markovnikov additions. Whenever the peroxide is present when you add an HBr, it follows the rules of an anti-Markovnikov addition. So what is anti-Markovnikov rule? We know that the negative part adds to the carbon which contains more number of hydrogen atoms. In the case of Markovnik, the negative part adds to the carbon which contains least number of hydrogen. So in this cases, the bromine according to the anti-Markovnikov systems, obviously the Br minus attacks to this particular carbon, because the negative part of addendum adds to the carbon which containing more number of hydrogen atoms. Markovnikov rule is the least number, whereas in the case of anti-Markovnikov, the carbon which contains more number of hydrogen atoms, there it will be added. So according to that, but anti-Markovnikov rule, the bromine will be attached to this carbon of this that has two hydrogen atoms. So according to the carbon which has more number of hydrogen atoms. So based on that, we will be able to obtain CH3, CH2, CH2Br. That means propyl bromide. So the free radical addition reaction, the best example I took is propene and react with HBr in the presence of peroxides, and it will be able to obtain propyl bromide as the product for this type of free radical addition reactions. Now we can see this mechanism of this particular reactions. So first step is this, in this particular cases, the peroxides undergoing the homolytic cleavage and form the radical. That is the first thing. And moreover, the peroxides will not obtain 100%. Always it is 70 or 75, 80 because some amount of water should be needed. Otherwise, it is propellant, it will be burst. It's usually peroxides or propellant. So, for example, the mechanism, the first step is RO, or maybe this is anything, benzyl peroxide, whatever it is, this first thing. So, it will be heated and it will be formed as a radical, and RO dot. We'll take it as a radical. First step is the formation of the radical in this case. The second one, you can see the step one. That means it follows this initiation, propagation, and termination. There are three different steps here. One is initiation, and then propagation, and then terminations. And then propagations, and then termination. So these are the three steps follows in the case of free radical addition mechanisms. So in the next step, automatically this RO dot is moving into this HBr. This is the initiation step actually. They're generating the radical now. So ROH plus Br dot. So that's the first thing. First thing, the generation of this bromine radical. Okay. And afterwards, then the propagation step, take this molecule of propene and react with this Br dot. So here you will be able to obtain so the mechanism goes here, the bond. So one of the atom moves here and one of the atom, bromine radical, that atom moves here and it forms CH2Br, and then another one more atom, one more electrons goes over on this carbon, and this forms as a radical here. Okay, this radical is a secondary radical. Suppose if this attacks in an other way, for example, you can say that's okay, you can write it in this other way. Suppose the Br dot, so it forms this one and this one, and with this dot is forming, that means the primary one. Suppose if this carbon and bromine bonds in second cases, and the CH2 will form as a radical, and this radical is called as a primary radical. There are two possibilities there, what I'm talking is. So in the case of propagation step in the one, either you can get a secondary radical or you can able to obtain as the primary radical. But theoretically there are two possibilities. But in experimentally, we will get only the secondary radical, because you know the radical stability is also tertiary, primary, secondary, and then primary. So based on this radical stability, obviously we will able to obtain secondary radical rather than the primary radicals. Okay, so that's why now I'm erasing this primary radical, because that will not have a possibility to form now based on the stability. So once this secondary radical is formed, now it will form an HBr again, and obviously this in this cases you'll be have this, and this bond will breaks, and you'll be able to get CH3, CH2, and CH2Br plus Br dot. That means this is completely cycle again and again. So the Br dot again attacks this fresh molecules and it goes. If polymer means it will be cycle. So this is the propagation step usually. And then the last one is called as the termination steps. In this case, possible is Br dot plus Br dot. You'll be able to obtain Br2, And some cases you'll be able to obtain or dot plus or dot, I mean radical, it will form or etc. It goes like this. So this, the last one is called as this termination steps. Okay, so that the case of free radical addition reactions, when you look at this, the mechanism goes in this way. It involves three different steps. One is an initiation, another one is the propagation, another one is the termination steps. The case of initiation, before initiation, first, I mean, the peroxides will cleave in a homolytic way and form a radical, and the radical first initiation step form react with an HBr and form this Br dot first. Then the Br dot will undergo the propagation step, react with the propene molecules, and obviously they will be getting this secondary radical. Then again that will be abstracts this hydrogen radical, and there will be, you'll be able to obtain the propyl bromide plus Br dot. This is like a cycle system. Especially in the case of polymer, it is absolutely continuously keep on its cycling the system. And then the termination steps is Br dot and Br dot, and that will be reactive and forming the Br2, and or otherwise the two, I mean, radical chains will be coupled and form this particular alkane product, etc. These are some of the side products. Okay, so this is an addition reactions mechanism, especially in the free radicals. Okay, so here also the application you can able to obtain this in the case of this application of this particular cases is also you can, it is also alkyl halides form main. So alkyl halide formation is this major one in this case of this application point of view, and also pharmaceutical intermediates and lot of polymeric process. Polymer, in the case of polymer industry, this particular free radical addition reaction is most preferred in this, but using this particular reactions. Okay, so right, so I would like to be conclude of this by saying the summary of this today's lecture, and today we have seen about this addition reactions and this particular lecture, and we have seen about the first the definitions of those particular addition reactions. The main thing is an attacking species, and most probably in this case pi bond always breaks and the new sigma bond is formed in this particular case of this addition reactions. Okay, there are different types of addition reaction we have seen. One is an electrophilic, a nucleophilic, and the last one is a free radical addition reactions. So depending upon the attacking species, these types summarized. I mean, types categorized. Attacking species is electrophile means electrophilic, and attacking species nucleophile means nucleophilic, and attacking species free radical means it is free radical addition reactions. And also we have seen the mechanism of each and every addition reactions, how many steps it is involved, and which step is the slow steps, and which step is the fast step. And we all know that, you all know that this slow step is always rate determining steps. So electrophilic additions also, we've seen two steps will be there, and we have seen in this one. And what are the possibilities for to form this so one product? For example, this in the electrophilic addition reactions, there are possibility of two products in the unsymmetrical cases, but we know that why other product is not formed and one product is preferred, and we have seen those kind of things as also. So these addition reactions mainly based on the two different rules. One is Markovnikov rule, another one is an anti-Markovnikov rule. Okay. And then application is mainly involve this, it's synthesis of an alcohols and also synthesis of an alkyl halides and pharmaceutical intermediates and industrial process and polymer industries. All these places, obviously this addition reactions is very much useful. This, I hope you all understand and enjoy this lecture for this 30-35 minutes, and I would like to thank you for all those who are watching this video, and I will again catch in the next video. Thank you very much. Thank you all.